Hi, everyone. My name is Xinyu. I'm actually from LinkedIn Streaming Infra team. So today I want to talk about actually how do we use Apache Beam and Samza to do large-scale stream processing at LinkedIn. So it's actually great. The previous talk is about Google Data Flow, so you guys can actually do a comparison of what we did and versus what's actually in the data flow. So the talk will actually cover four topics. So first, we'll do a short introduction of Apache Samza. So basically, you guys pretty much already aware what is Beam and what is the other runners like Spark, Flink, and I would like to talk a little bit about Samza so you have an idea of what it is. And then we'll do a deep dive to see how do we actually run Beam pipelines at scale on Samza. Later, we'll cover a few use cases at LinkedIn. So these use cases are actually typical examples. How do we run Beam pipelines? And finally, we'll cover our roadmap. So about Apache Samza. So Samza was actually developed earlier in 2013. It's actually shortly after Apache Kafka. You guys are probably all know Apache Kafka, which is like a big data pipeline system. You can actually use it to transport your data in large scale with a really good throughput. So Samza was developed as a processor tool to actually help you to process your real-time data, do some data analytics, and also do some aggregation on top of your data. So basically, we're looking at something you can actually get the results in a very short amount of time, so with like low latency. So Samza becomes a Apache top-level project in 2014. And after that, we have 10 major releases. And today is actually 1.2 version. And we have like over 20 kind of committers afterwards. And the users of Samza are mostly companies in the United States. You see, like beside LinkedIn, there's Intuit, Slack, and TripAdvisor, and obviously there's quite a few companies actually using us. And what we heard, actually, they're using it to cover a lot of different use cases, from actually high performance kind of splitting message to different services, to actually a more complex thing which they accumulate a large amount of data and actually a large amount of state to actually do some meaningful processing. So that's how Samza was used today. So this is actually a specific view of how Samza was used in LinkedIn. So inside LinkedIn today, we have over 3,000 applications running in production for Samza. And these production jobs actually are coming from domains like security, doing like fraud detection, or actually doing like real-time messaging, and also machine learning use cases like signalization, or actually feature generation, all these kind of things. And today we're processing 1 trillion messages per day inside LinkedIn. So it's actually, we got like messages from different sources like Kafka or Brooklyn. Brooklyn is actually our change capture stream. So you know, like when a database actually publish those change logs, we actually stream those change logs into a kind of a stream, and then the data is getting populated into different services and actually different places inside LinkedIn. We also actually consume AWS Kinesis and Microsoft Event Hub, actually those kind of stream to actually process it. So that's actually sum up to 1 trillion messages a day. So the Samza cluster inside LinkedIn has over like 30,000 machines. And we use quite a few different cluster like a management system inside LinkedIn to actually process. So we have like the traditional Hadoop Yarn cluster, and we have a standalone Samza cluster which use ZK for coordination, and we also use Microsoft Azure and Kubernetes. Kubernetes is actually in the works. So with so many kind of applications and so much traffic, we still want to have like high availability, because any fraction of downtime can cause a huge impact to our services. So we do a lot of things, which I'm going to skip right now, probably going to cover in the later slides. So from the previous talk, you probably already noticed Samza is actually mostly focused on scaling. So we're looking at low latency processing, large state, and fault tolerance, and fast failure recovery, all these kind of things. And that's the reason why we actually adopt Beam. Beam gave us a nice API, a very powerful API and processing model. And also, we leverage Beam's portability framework to support Python and Go. There's actually a talk on Go, which was very interesting. And the SQL, which has been mentioned like 1,000 times right now. So we actually want to use that too. And there's MR libraries we want to use. So now we will take a deeper look at how we actually execute Samza, execute Beam pipelines on top of Samza. So this is actually a diagram of the whole streaming ecosystem inside LinkedIn. So the really top tier is actually our application services. There are actually thousands of applications running inside LinkedIn, trying to provide different kind of service to the users. And the application service actually generates data. So these data gets pushed inside Kafka or inside different databases, and or like all these Espresso are homegrown database. There's Oracle, MySQL, and Embry. All these are actually databases. And they're also pushed down into some kind of key value store. So all these, the Venice, Pentinode, all these are actually our own key value stores. So these data sources actually, we want to process actually these data and give user results in a very low latency manner. So that's how actually we use Samza and Beam here. So typically we consume real-time data from Kafka streams or from this Brooklyn stream. Brooklyn is our change capture stream, which actually listens to the database change log. So these real-time streams getting pumped into our streaming pipelines. And also the results can be actually joined with actually the key value stores. So we do actually real-time lookups on these key value stores and then join them with the real-time input. And then we generate results and back into these data stores. So this is actually a typical stream processing ecosystem inside LinkedIn, and many of our applications actually inside this ecosystem. So that deeper look of how we actually run Beam pipeline on top of Samza. So the translation of Beam pipeline to Samza is actually very close to Flink. So basically, it's just how we translate the destination operator is actually going to be Samza operator. So for example, the IO.read is actually translate into a Samza source system. So we have two source systems handling different sources, like unbounded sources and bounded sources. This is actually very close to Flink. So, and Purdue, all these different transforms, the primitive ones are actually getting translated into our own operators. For example, Purdue is translated into a do function operator, which actually we support both legacy kind of Java transform and portable transform using different do-func runners. So there's a simple do-func runner for the legacy ones, and then there's exhibit stage do-func runner for the portable ones. And Windows is the same. And group by key, we actually translate to a group by key operator using this function do-func with the really long name, but that works pretty well for us. And something to notice is actually in both Purdue and group by key, we integrate with our own watermark and state and timer backends. So basically, from the source, we populate both the data and the watermarks. And then in do function, or in actually group by key, we actually use this watermark to trigger it and keep the things in our own state and trigger by our own timers. That's actually how things work in Samza runner. So in the end, it's going to translate into a Samza operator DAG and gets executed in a Samza cluster. So this is actually a deeper look of how we execute the pipeline in the Samza cluster. So I know there's a lot of ways to actually dissect the data. So there's like in Spark it's called splits, and in actually Google Dataflow it's called short. And in Samza, because we come from the Kafka camp, it's called partitions. So basically we group the same partition into the same task. For example, in here, we have two input streams, and the partition 0 are grouped into the same task, which is partition task 0. And the task is actually a kind of a basic level to actually process a single partition. And also we group tasks by containers. So container for us is actually just a physical kind of a unit to allocate resources. So you can say, like, I want how many CPU cores for a container, and how many memory for a container, and how many threads. So that's actually the way we allocate kind of physical resources. And the containers are coordinated by something called a job coordinator. So this guy actually does periodically hard bidding for different containers, and if there's any like container failure, it's going to restart the container. So that's how a Samza cluster works underneath. So in terms of scaling, there's two things actually very important. So one is actually parallelism, the other one is actually state. So actually I'm going to talk about both. So parallelism in Samza is actually, we have like 3 levels. So first level is called like container level. Since container is actually the way we allocate resources, itself is actually running as a just JVM process. So for example, there's like 4 containers that be like 4 JVM processes. And inside the container, you already see there's we can allocate multiple tasks. And these tasks can run in parallel. So here we see like 3 tasks actually processing 3 partitions and running in parallel by itself. And due to like whatever the do function or group by key, the state is actually key based. So in order to achieve better parallelism on top of like this key basis like system, we actually can allocate workers based on keys. So you can actually create like a key executor actually to actually create worker threads to process keys from different key spaces. So that's actually give you a better kind of parallelism by itself. So state. So this is actually a very interesting question. So far, quite a so it's like Samza does state is a little bit different from a lot of other runners. Actually, that's a kind of a distinguishing fact. So, because what we found inside LinkedIn is actually most applications, if they're doing some complicated processing, the state they require a huge amount of state. So here we have an example. Some applications actually use 1.2 terabytes of state by its total. So holding those state in memory is actually very challenging. It causes a lot, like large amount of GC, and it causes some kind of pure problems when you actually like when you do a failover of this entire job. So the way Samza approaches this is actually we use a on-disk key value store, which is RocksDB, to hold the state. So this gives us a very best, like one of the best performance to actually access your internal state. And since it's local state, we have to persist it, because if the container failed, it won't be able to actually restore state if there's no persistence. So the way we did it is actually the state, every update to state is actually published to something called a changelog. So the changelog contains the history of all the transactions you've done on the street. And then if this container failed, we'll recover everything, every single operations on the state from the changelog. So we can fully replicate the state from changelog in a different machine. So that's actually how we process the state. So local state does give us a very good performance benefit, as I talked about earlier. So as we test by some benchmarking, it is actually 100 times faster than using a remote state, which is actually critical for a lot of our jobs, because LinkedIn's traffic is actually pretty heavy. So it's like not even possible to actually go remote to do a remote code to update just the state. So in terms of remote calls, we actually built a table layer on top of the existing API and actually facilitate some other remote calls. Because every time if you do a remote call, it's actually very costly compared to actually a normal like a local lookup. So we built a caching layer which allows us to cache like most recent items when you read from remote store. We also built like relimiting, so the application service will not DDoS the services, and also the batching, which will help actually to retrieve the data in one single shot. And all these are while in Purdue. So basically, in the init, we actually create the connection to remote store and process element. We are able to look up the items. So this is actually a typical way to do join using Purdue. And then finally, we are able to output the Peck collection based on these based on our table layer. So our users actually are using this quite a lot in our own applications. So the other thing actually I want to talk about is actually checkpointing in Samza. So I know different runners have their own ways of checkpointing, and this is actually very unique in Samza because checkpointing we all have our own speed. So checkpointing for us is actually we don't checkpoint the full state. Because you think of this, it's like 1 terabyte of state. It costs a huge amount of time if you do a full copy of it. So what we do actually when we do checkpointing is actually we do something called incremental checkpoint, which is actually we only process actually the state change from the previous checkpoint to the current checkpoint. So if you look at this, it's actually in task 0, there's 8 messages between the previous checkpoint and the new checkpoint. So those 8 messages are going to be processed in our change log. We also write the change log, the checkpoint mark in the checkpoint stream. Those things will be written together. So checkpoint for Samza is actually very, very cheap. So usually it's like a milliseconds level kind of checkpointing. But it does have one performance kind of drawback when you actually restore the state. So because you are going to read the whole change log stream in order to fully restore your state. So we did quite a few optimizations on that too. So first, we we use some mechanism called host affinity. So this is actually when we actually try to restart a container, we always choose the same host as a preferred host to restart the container, because in this way we can reuse the state from previous run. So that gives us reconstructing the whole state within a few seconds. So basically by comparing the local state with the change log and actually filling the delta as the gap. So if we are not able to use the previous host, which means either the resources used up or previous hosts actually have some failure, so we use 2 other mechanisms to help actually restore state. First is actually the state is recovered in parallel. So every single state for each task is actually recovered itself, but in parallel, so you actually won't get a sequential behavior. And the other way is actually, if you look at the changelog itself, we use something called log compacted Kafka topic. So basically, all the updates to a single key will be compacted together. So we will not, when we actually restore, we will not actually go through all the updates to this particular key. It's going to be just a single update. So that's actually what we use for actually restoring. So with these kind of optimizations, even recover from a remote host, we will actually be able to restore state within a few minutes. So Samza's currently how we run Beam pipelines is actually we use Yarn cluster very often. So this is actually when you do a pipeline.run, the whole pipeline is actually translating into a Samza job, and it gets submitted in a Samza Yarn cluster, which actually is going to be distributed into a Samza Yarn nodes and creating containers. So we use Yarn for resource isolation and multi-tenancy, all these things. And aside from that, we also have our own standalone cluster, and the coordination is done by Zookeeper. So here, actually, we use Zookeeper to do some leader election, and then create a job model, which knows each Samza processor to choose different partitions to process. And after that, they will be actually running in parallel to process the streaming data. So these 2 are actually the majority of the things we have, and we are actually currently working on deeply integrated with Azure to use Azure itself as a clustering management system to deploy Samza jobs, and we're also working on Kubernetes. That's the current way. So it's hard to talk about running a pipeline without talking about observability, and it's actually the previous talk a lot about auto-scaling. So I'm going to touch upon a little bit about auto-scaling, because right now it's not open source. It's still actually used internally inside LinkedIn. So we do auto-scaling in 2 kind of aspects. First, actually, when you first deploy a Beam pipeline, you have no idea how this Beam pipeline is going to run, right? So how many actually containers, how many resources you need to allocate. So the way to figure it out is actually we use some kind of static initial sizing. So we know how much QPS, how much traffic you're going to put in your input topic, and what kind of structure you're looking at, like how many group by key, how many shuffling you're doing for this particular pipeline. So based on that, we have some estimate how many physical resources you need. And in runtime, we are going to adjust your physical resources based on metrics. For example, whether your process is lagging by some kind of a matrix, or you have like hot partition by like certain CPU and the memory matrix. So that actually we are going to adjust your physical resource during runtime. So right now we're still working on this part. So basically we're focusing on a non-stateful kind of applications. So and we're actually working on the stateful applications too. So Samza already also provides a error diagnostics like service. So this service will give you an idea if there's errors in your application or if there are exceptions in the applications. It's an easy way for you to look at to see anything happens actually based on some kind of log trail. And the other important part is actually if you want to actually do something for your application, we provide some kind of self-serving kind of service. So basically, if you want to, I think somebody mentioned in the other talk, if you want to rewind your pipeline into a previous time, it's going to be very hard today for a streaming job. And we offer some kind of checkpointing service, which you can literally say, this is the time you want to rewind your pipeline to, or there's the offsets, or actually the checkpoint marks, you want to rewind your pipelines. And then we'll actually proceed to process from that point. That's actually one way we provide to our users. And we also can able to actually move the containers on demand. So given like we are running in a pretty large cluster, some of the CPUs and memory is getting they're competing with each other. So it's actually a good thing to have to actually be able to move your containers around. And failure recovery. So there are quite a few applications inside LinkedIn are very mission critical, meaning that downtime of a few seconds might impact a lot on the LinkedIn business. So what we actually provide is actually we have hot standby containers. So basically, if the main job has any failures in some of the containers, it can immediately switch to a hot standby containers. So meaning the downtime will be actually very small, which the hot standby standard actually has the full replica of your state and whatever associated with it. So here's a few use cases actually I'm going to cover. So which you guys actually probably heard use cases from other companies. This is actually a use case from LinkedIn for Apache Beam. So the first one is actually on the security team. So they use Beam, actually, this is Beam pipeline, to do some fraud detection. So in the input is actually a stream composed of all the user activities. So, millions of users are clicking in the LinkedIn website every day. They generate a page view event. They generate quite a few, when you reply a message, when you do likes, comments. All these events are creating this user activity stream. And when the stream actually comes inside, we want to be able to tell there's some fraud in some users. For example, there's spammers, there's actually bots. There are quite a lot fraud activities. So the way we actually try to do is actually we try to separate the fraud in the user activities by clustering. And we use a session window first to actually group the user activities by a session by its own ID. And once we've done the grouping, we create the cluster mapping. So the cluster type can be like a cookie. For example, this is the user actually using how many cookies within this particular session. Or cluster type would be an IP, so how many IP addresses can user have within a session. So for example, you can imagine when you actually, one user, when you have a bot, it will be sending multiple different kind of requests, but the IP address is the same. So that's actually one way to tell a bot or like a spammer. So once we done the session grouping, we have a pretty good idea of for each user what kind of cluster they have and what kind of the data they are actually belongs to. And then we send the unique clustering data into a user clustering stream, which gets joined with a cluster labeling stream. So the labeling stream actually is coming from our online services, which can tell whether this cluster is good or not. So basically, we found a cookie is bad or found like IP address is bad. That's actually the signal to tell there's a clustering problem. So based on these two data, we actually do a join using stateful Purdue. And this actually particularly join will figure out based on each cluster, how many users actually are using it. And we can measure the size of a cluster. We can detect if the cluster is actually bad based on certain part of the cluster is bad. For example, if one cookie is bad, you know the whole cluster might have problems. So for example, you detect that cookie belongs to a problematic user. So once we have that, the whole thing will actually send into a class scoring mechanism, which does kind of a machine learning kind of model, uses some machine learning model to score a cluster based on different types. So, and then if there's any kind of like flow find, it's going to emit the result. So that's actually one of the pipelines used in flow detection. And this is actually and there's another use case from the machine learning teams. So in this team, actually, the request is actually pretty interesting. So data scientists, they're not happy to write code. They want to write simple DSLs. And this is actually, for them, even easier to actually just write the definition of features. So they want to say, yeah, for this particular feature, I want to know I know what's the input, what are the fields I want, and what are filter, and windowing, all these kind of aspects of this feature. And we allow them to just define the feature in just a standard format. And then internally, we generate a Beam pipeline on top of this feature definition. So this is actually a simple pipeline generated. So you see, like, we generate IO read from source, we apply filter, we apply select, and eventually we do some grouping based on it. And the output can be user-defined kind of either a Kafka stream or remote data store. So this helps a lot, because it drastically reduces the time of our data scientists to actually creating features and experimenting with it. So that's one way we actually doing in our machine learning teams. And there's another kind of a use case very interesting is, I know there's one of the talks mentioned about using Peck. And Peck is actually very outdated, as you can see. So many of them might know Peck, but don't use it anymore. LinkedIn has this actually, because the legacy reasons, we still have thousands of Peck scripts lying around in our teams. So it used to work pretty well. Actually, we use Peck script. A lot of these scripts actually are used to generate metrics. So like reporting some certain business critical metrics to the executives and to actually other people. So the problem with the current Peck script is not Peck is complex. It is because actually the processing in batch mode, which is lagging behind. Usually it's like 6 hours, like half a day or even a day behind. So for the business users, they actually want to see a more up-to-date result. So for this work is actually very cool, because it's actually translating a Peck script into a call-side logical plan. And this logical plan was actually further translated into a physical plan and then generate Beam code on top of it. So basically, user doesn't change anything. The legacy script is still there, but we actually end up running as a Beam pipeline in Nearline. So you actually can see it actually more real-time result. So my colleague actually did this work. So if you guys are interested, he published an engineering blog on top of this. This is actually pretty cool work. He's gonna contribute back to both call-side and Beam on the things he did. Actually, this is actually pretty cool. So last, I want to talk a little about our roadmap. So I think a lot of talks in the session is actually focusing on portability and Python. So that's the same for us. So one of the most things we like about Beam is actually portability. And for us, the basics are done. So we already support like Purdue, group IQ, all these actually in a portable manner. So we can run a simple Beam pipeline pretty easily, like word count. And what are missing is actually the state is not user-defined state, timers, side input are not integrated. And we also need to do some performance enhancements, like Flink Runner, for example, bundling. And then we'll also need to integrate with all our cluster deployment, for example, Yarn, Kubernetes, and this stuff, and adding the test to it. So regarding to Python actually, we are already actually using it, and there's going to be a Beam jobs in production pretty soon. So we're going to actually, we benefit a lot from Flink Runner on this, because we learned a lot from Thomas. So pretty nice. So our users are also trying out different machine learning libraries on top of Beam pipelines, trying to actually be able to benefit from that. And also we need to integrate Python test. Regarding to Samza itself, since now we're looking at more ways to run it and more better like scaling and other parts. So we're looking at integrated, for example, with Azure, integrated with Kubernetes, and also we want to be able to have a full kind of auto-scaling story in open source, so making us being able to handle like really nice traffic and with reasonable resources. And we also, so LinkedIn is actually doing a lot of async processing. So I'm not sure what you guys are actually using async. So for us, async is like one thing to talk our services. All the service calls are async. So we want to actually build async API on top of Beam. So this can be leveraging on both our other users as well as the Samza users. So that's all for the talk. Thank you very much. So any questions?
So you talked about feature engineering, right? Are you storing those features for future reuse for a different data science use case, maybe? Do you have some kind of a feature store available?
So you mean mostly for data scientists?
Yeah.
So we're doing like two parts. So which actually is deeply integrated with the current Beam API. First is actually what's shown here, which is actually generating features. So generating features is actually we want to fully optimize the pipeline, being able to generate features by different, just a few definitions by data scientists. The other is actually trying to consume features.
Okay.
So consumer features is actually we use our own like feature store inside LinkedIn to consume features. And then the feature store is actually backed by different physical stores. For example, you have a key value store, you have like remote database. All these are integrated.
I get that. And the other use case is you talked about online clustering, section 1, section 2. Is it all in Java or Python? And what are you using for the clustering?
Right now, it's actually all these are actually already production use cases are in Java.
Yeah.
So the first Python case is actually going to be using some scrolling using TensorFlow. So that's our use case. So basically, the Python use case is actually trying to do some text extracting from videos. So that's actually using TensorFlow models. So,
And you're doing a clustering on stateful, what is in state, right?
Yes. Everything is actually, all the aggregation, the results are in state.
So if the state keeps getting updated, how do you update your clusters? That's what I'm trying to figure out. Is it an online learning algorithm?
Yeah, exactly. So basically, we send updates to the later scoring service, which will actually keep scoring on the update state.
So the first version of the model would be from the first state that you store, is it?
We usually burn the pipeline for like over an hour, over a week, trying to get some statics.
Unfortunately, we ran out of time,
Okay, sure.
but thank you so much for your talk.
Thank you, guys.